Now I am going to start with economic operation of power system. This is your PSOC's unit number 4, economic operation of power system. So the following contents are available in your unit number 4. Statement of economic dispatch problem, input and output characteristics of thermal plant, incremental cost curve, optimal operation of thermal units without and with the transmission losses, no derivation of transmission IOS coefficients, base point and participation factor method, statement of unit commitment problem UC, constraints on UC problem, solution of UC problem using priority list, special aspects of short-term and long-term hydrothermal problem. So these are all the contents you have in your unit number 4. So in PSOC paper, what you have learned so far, you learned about your preliminaries on power system operation and control, the fundamentals, the basic power scenario, national level, international level. So what discussed in unit number 1. So likewise in unit number 2, real power frequency control we discussed. We have a lot of methods, single area system, 2 area systems. And then unit number 3, reactive power voltage control. You learn the third unit topics also, the implementation of fax devices in your power system. Now, the unit number 4 and 5 belongs to your application of the above mentioned units. So economic operation. So economic operation highly needed for each and every power system operation. So you know about your fundamentals, you know about your control system, everything, but we should aware how to operate the power system in the economic mode. So that is most important. So the economic operation is one of the application of power system. And next one is the advancement of economic operation is implemented in your computer control. So we may monitor, we may analyze, we may record our data in terms of your computer control. So how it is possible means through economic operation. Once you fix the economic operation, so it should be infused in your computer processes. And it is monitored, analyzed, and recorded everything. And based on that performance, we may behave. So the economic operation plays a vital role. So one of the most important term needed in the industry sector, in power sector industry sectors. So the economic operation is most needed. So some fundamentals I'm going to introduce to you. So economic, what is meant by economic operation of power system? So what is the main objectives of electrical supply industry? People calling as ESI. So electric supply industry. There are both public sector as well as private sector involved in it. So the main intention of using the electric supply industry is their main motive or objective is to minimize cost and maximize efficiency. So with a minimal amount of cost, extracting maximum efficiency. That is most important in your economic operation. Second one is reliability. So reliability means throughout 24/7 you are getting the supply, continuity of the supply. And third one is security of the supply, whether the supply is secured, highly secured, without harming to the environmental factors. Last one is sustainability. So these are all the 4 main objectives of your electric supply industry. So a compromise is sought which must not jeopardize the safety to personnel and equipment. So we never compromise on your safety in terms of personal as well as equipment. So we need all our equipments, all our human should be in a safety manner. So in that manner, your electricity supply is circulating to everyone. So the action required. So what are the possible actions required for that operation? Long-term load forecast. So the load forecasting should be in the long term. So it should be futuristic. Suppose our population in India is more than 100 crores. 10 years or 15 years, it might be 120 crores, 130 crores. So based on that, we have to forecast our load and the development of network. So we have to improve our network performances also to increase the buses. And then short-term load forecasting is also needed. Suppose in case of emergency, we are focusing on the short-term load forecast also. So in power system operation and control, we have voltage regulator, automatic voltage regulator. So what is the role of automatic voltage regulator? It controls your reactive power as well as voltage. That is the main purpose of AVR. And next one is turbine speed governors. So the main purpose of your TSG, turbine speed governor, is control of your real power as well as frequency. And third one is optimization of power system operation. So the main purpose of studying power system operation and control is these are all the various methods. You have to regulate the voltage, you have to control the speed, you have to optimize your power system. And load characteristics. In order to make the best utilization of power system and available resources, you should aware of the loading condition and characteristics of the individual loads are essential. Should be keep eye on all your loads. Should be aware of all your load performances. So loads may be characteristic in regard to size. Size means watts to megawatt. A சின்ன செல்போன்ல இருந்து பெருசா யூஸ் பண்ற பவர் சிஸ்டம் வரலையும் we have to incorporate the size watts to megawatt. Next one is symmetry. Either it should be single phase or three phase. And third one is load consistency. So with respect to time, frequency, and voltage. Fourth one is use cycle. Whether the cyclic process should be a regular mode or random mode. So symmetry between three phases can be achieved by intentional distribution of single phase load. So these are all about your load characteristics, and you may have the load curve like this. In first unit, you may studied about curves based on the corresponding demand with the time intervals. You may propose your load in terms of your bar charts. Bar மாதிரி போட்டிருப்பீங்க. So இது வந்து throughout the seasons. So summer, typical summer, winter, typical winter. So the utilization of loads is really depends upon your seasons or climate. So அதுக்கேற்ற மாதிரியும் வந்து பார்த்தீங்கன்னா we have to economize our power system. நம்ம winter seasonsல we are utilizing very less amount of energy. But in terms of summer, we are using more amount of energy. இந்தியாவை பொறுத்தவரை சரியா அங்கே வந்து ஃபாரின் கண்ட்ரிஸ்ல வந்து பார்த்தீங்கன்னா விண்டர்ல தான் அதிகமாக யூஸ் பண்ணுவாங்க. they are using heater loads. ரூம்கே ஸ்பேஸ் வந்து பார்த்தீங்கன்னா ஹீட்டிங்க்கு அவன் ஹீட்டிங் லோட்ஸ் கொடுப்பான். நம்ம எப்படி ஏர் கண்டிஷனர் வெயில் காலத்தில் யூஸ் பண்ணுறோமோ அவன் வந்து விண்டர்ல ஃபுல் அண்ட் ஃபுல் ஹீட்டர்லேயே இருப்பாங்க. Support your load for time versus demand for all your monsoons. Load factor. So load curve is the plot of variation of the load demand with respect to time. The peak or maximum demand is defined as the maximum load occurring in the time under consideration. Load factor may be defined as average load to maximum load during the same period. these things you may study in your number 1. The fundamental things needed in the economic operation also, load factor, average load by maximum. Or mathematically, I can say energy consumed during a period of time divided by maximum demand into time under consideration. So you can define your load factor by daily basis or annual basis. In some cases, quarterly, half-yearly is also possible. So our utilization should be the daily or annual. Diversity factor. So diversity factor is applies to a group of loads if diesel maximum demand do not occur at the same time. So it is for your industrial, commercial, and domestic loads. So what is diversity factor? Definition is sum of maximum demand of the individual consumers to maximum demand of the system. So always it should be greater than unity. Utilization factor. So utilization factor shows how well the plant is being used. So it's the ratio of maximum demand to utilization installed capacity. Normally, the percentage of the estimated maximum demand and reserve capacity to provide better reliability. And additional generation capacity should be improvised and the hard standby. So hard standby in the sense about 30 minutes of reserve capacity should be provided in the power system. Demand side management, DSM. The objectives encourage the consumer to use less energy during peak hours. So load curves lose the peak points. How it is possible, how you achieve the demand side management is shift the demand from peak times, that is night times or weekends. Incentive is change of tariff or use smart metering to advise on best tariff rate at the times. And the optimization methods, these are all the optimization methods we are having. Economic load dispatch or generation scheduling, minimizing transmission losses, computers with optimal portfolio programs are used. The factors considered for operating your system in economic mode is fixed cost of supply. For example, interest, fixed salaries, and depreciation. Second factor is variable cost of supply, that is utilization of fuel. And third one is transmission losses. Fourth one is transportation of fuel. So the optimization is established on daily, monthly, or yearly basis. Next one is economic dispatch. To achieve the economic dispatch, variable cost, although the fixed element of the generation cost affects the overall cost of the production. It's not normally considered in allocating generation to meet. Allocation is based entirely on the variable cost. So we have to consider the fuel cost, generation efficiency, maintenance cost, etc. And then heat rate characteristics. So thermal performances also you have to evaluate during the some operation in economic mode. This is the heat rate characteristics, the heat versus your power. You may get the linear characteristics when it is a theoretical case. Practical, somewhat it is lacking. So economical division. So economical division incremental fuel cost for all contributing carbon generator sets should be the same. If two sets having different fuel costs are shared a load, the total cost can be reduced by transferring load from set having the higher incremental cost to set with the lower incremental fuel cost. So this decreases the incremental cost of the former, increases of the latter. So two incremental costs are equal and total cost is minimum. So this is your economical division. We have to divide our systems into increment as well as decrement. So example from we are not solving, but we have a pattern like this. Our power plant consists of two generators that having the following fuel cost F1 and F2 in shilling per hour. நம்ம இந்தியன்ல வந்து ரூபி per hour வரும். So F1 is 0.0115 P1 square, 9.3 P1 plus 90 for 0 P1 less than 100 megawatts. The maximum limit is given. Likewise, second power plant F2 is 0.01 P2 square, 8.2 P2 plus 80 for P2 is less than greater than or equal to 200 megawatt. So P1, P2 are in. So the power plays a total load of 1 by neglecting the losses. We have fuel cost for F1, F2 given in terms of your P1 and P2 in terms of megawatt is given. So the total is given. P1 plus P2 is 150 given. So you have to neglect the losses. So in that case, you have to determine what is the power supplied by each generator. If these generators are to be operated in the mode of the optimal dispatch, if it is operating in the optimal mode, what is the power supplied by each generator for plant 1 as well as plant 2? And the second determination is the savings in fuel cost in Shilling per hour. The plant is operated in the optimal economic dispatch mode compared with equal load sharing. So whether the load is shared equally or not while you are operating in your economic mode. So that is the first exercise you have. So we are going to solving these kind of problems in our examples. And second example. So installed capacity of the generators is 150 megawatt. So generators they are given. They are not mentioned how many generators connected, but generators 150 megawatt. Generators supplied power to an industry load having the maximum demand of 140 megawatt. If the capacity utilization factor of the generator is 70%, determine the reserve capacity in megawatt. Reverse margin in percentage. Okay. And provide your comment on adequacy of reserve margin. Load factor, annual energy kWh. If the load factor is improved by 10 factors, I recommend one method that can be used for this purpose. Likewise, you have another example. The annual peak load is 30 megawatt power system is megavolt power system is 25 megawatts. Power station supplied load having maximum demand of 10 megawatt, 8.5 megawatt, 5 megawatt, and 4.5 megawatt. The annual load factor is 45%. How to determine the average load, electric supply per year, diversity factor, capacity factor. Yeah. So these are all about your fundamentals of economic operation of power system. Now we proceed with our syllabus. So the first topic is optimal operation of generators on a bus bar. So generator operating cost, nothing but total generating operating cost, which involves your fuel cost, cost of transmission line, labor and maintenance cost. So the topic itself, they clearly mentioned optimal operation of generators on a bus bar. We are just concentrating on your generator as well as bus bar only. Okay. So if you are calculating the loss operating cost of generation, it includes your fuel, what kind of fuel that you are using. Either it may be nuclear fuel or a thermal fuel, whatever it may be. Cost of transmission loss, we have to calculate labor and maintenance cost. For simplicity, fuel cost is considered to be a variable F. On the problem path only, F one. The fuel cost is meaningful in case of thermal and a nuclear power station. But for hydro station, it is not applicable. Why it is not applicable? Energy storage is apparently free. So based on the stream of your water, the storage is not permanent. So it is not applicable in case of hydro stations who doesn't have any fuel because it is a natural resource. So it comes under your renewable also. So cost of generation depends on operating constraints or system constraints. So first constraint we are going to evaluate equality constraint for real power as well as reactive power. So for real power, P suffix P is summation Q equal to 1 to N EP into EQ GPQ minus FP BQ plus FP FQ GPQ plus EQ BQ. So this is your equation 1 for real power equality constant, first equation. This is the general expression which you obtained in your power system. Next one is a reactive power QP. So Q equal to 1 to N. So this element should be modified here. And the reactive means negative signs. So FP EPGPQ minus FP BPQ minus EP FQGPQ plus EQPPQ. Equation number 2. So where VP is nothing but EP plus J times of FP. So YPQ is nothing but GPQ plus JPQ. This conductance plus acceptance or admittance, the transmission line. So previous one is equality constraint. Second is inequality constraint. So in inequality, you have a lot of subdivisions. So first one is generator constraints. So in generator constraints, first we have to consider KVA loading. So KVA loading mathematically it is given as PP square plus QP square should be less than or equal to CP square. So CP is nothing but pre-specified value of both powers. And second one is PP minimum is less than or equal to PP is less than PP max. So PP minimum is governed by thermal condition and PP max is limited by flame instability in boilers. Third one is reactive power limit, maximum to minimum. So maximum reactive power operation or generation is limited by overheating of the rotor. So minimum Q generation limited by stability limit of the machines. So here we have to check our reactive power limit, real power limit, as well as the overall loading should be the specified value. Second constraint is voltage constraint. So voltage constraint is VP minimum less than or equal to VP less than or equal to VP max. So most of the system would not operate satisfactorily and requires stabilization. So the load angle minimum to maximum limit may be provided. That is V is the voltage, L is the load angle, and C is running space capacity constraints. So the total generation G is greater than or equal to your PP specified, that is your real power specified in the plant plus spare. So spare means the reserve capacity. So the reserve capacity is half an hour is included. In some cases, it is 45 minutes or 15 minutes. So based on the requirement, the spare power is fixed. So first is during forced outages of one or more alternators in the system. And second one is unexpected sudden load on the system. And subdivision D is transformer tap setting. So the transformer tap setting, this auto transformer variable ratio is from 0 to 1 only. It is not below 1 or above 1. Two winding transformer tappings and secondary is 0 less than T or N number of buses. Here N in the transformer is transformation ratio. And the phase shifting transformer QP minimum, which is maximized, that is QP max, the limit. So Q is nothing but phase shifting angle. And the first subdivision is transmission line constants. This reactive power flow. Reactive power flow is limited by thermal capability of the system. TP less than or equal to Cmax. So your normal operating coefficient should be equal to your maximum loading capacity. And sixth one is network security. If there is no outage, then all the constraints must be satisfied. Even with one outage, constraints may not be satisfied. So line by line outage should be considered. Based on this results, proper security system should be provided. So these are all the steps which involved in your inequality constraints. So in equality constraints only you have to consider the real power and reactive power only. But if you are considering the inequality constraint, you have 6 parameters. We have to consider for generator, voltage, running space, transformer, transmission line, and the security of the network. 6 parameters you have to consider in inequality. And now, input-output characteristics of a generating unit. So it specifies the input energy rate. So it is generally specified as FIPGI. The unit is mega kilocalorie per hour, or cost of fuel used in EIPGI. It is rupees per hour as a function of generator power output PGI. Now I am considering as two functions. Fi of PGI should be your input energy rate, and second is CI of PGI should be your fuel cost, rupees per hour. So PGI Fi is mega kilocalorie per hour. CI PGI of fuel cost rupees per hour. And this is the typical input output characteristic of your generating unit. MW minimum is minimum loading limit. MW max is maximum loading limit. So the curve is between output power versus your operating cost of your or input energy rate. So the minimum to maximum calculation is possible here. At the time of starting, it should be falling. So it rises to the maximum demand, that is the maximum power which you do. So from these two limits, we are going to calculate our constraint values. The heat rate curve. So HI of PGI be the heat rate mega kilocalorie per megawatt hour. This is the heat energy obtained by conversion of fuel mega kilocalorie to generate 1 unit of electrical energy. This is the MW hour. In our domestic, we are using kWh, kilowatt hour. In case of power system, high capacity of power systems, we are using MWH. Here, output power versus your heat rate. So you may get a parabolic characteristic. So in parabolic characteristics, we are going to estimate the optimum operating point. So if I am assuming this point should be the optimum point or a nominal point, so I have to extend my curve to the heat rate as well as your output. So I have a balance here. So it should be defined as your heat rate. Put in rupees per hour by output in megawatts. So in general, the value should be 2.5 mega kilocalorie per megawatt hour. So normal heat rate operation. This is for your new applications. Yeah. Whether heat rate incremental is not corresponding change in output in any operating point. So my operating point as F. Next one is operating definitions only. Defined as of electric energy or output generated to fuel energy input. So 1 mega calorie is nothing but 1.16 megawatt hour is the electrical equivalent of heat. Next, incremental efficiency. The incremental efficiency is defined as the reciprocal of incremental fuel rate or incremental production cost, and is given by. So it is given by eta del P by del F. Ratio of change in output to the corresponding change in input at any loading or reciprocal of incremental heat rate. And next one is fuel energy input. fuel energy input can be obtained from the heat rate curves. So Fi of PGI equal to PGI HI mega kilocalorie per hour. So I'm naming expression as. Now we are going to determine the cost function. In terms of cost, we have to evaluate our functions. So cost of the fuel Pk, just fixing the constant of K, rupees per mk calorie. The input fuel cost Ca of PGI is K times some constant. The cost of the fuel is unknown to us. So time being, I am fixing as K. K times of FIPGI rupees per hour. So Ca is the cost expressed in rupees per hour of production energy in the generating unit. On substituting this equation in 3, you may obtain Ca PGI equal to K PGI HI PGI rupees per hour. Fourth equation. And next one is your heat curve. Heat rate curve may be approximated as HI. So Ci dash by PGI, Pi dash, Ai dash PGI. So from your heat rate curve, this expression is obtained. Equation 5. So the initial portion of the curve decreases, reaches minimum point and then increases. So in heat rate curve, you may observe that. These are so Ai dash, Bi dash, Ci dash are positive coefficients. So now I am substituting all the values in the input energy rate Fi PGI. So Fi PGI is nothing but PGI into HI. So here PGI is common. Ci dash by PGI plus Bi dash, Ai dash PGI. So if you are simplifying further, Ai dash, Bi dash PGI plus Ai PGI square mega kilocalorie per hour. So here we are achieved a quadratic expression in input energy rate. Next one is fuel cost PA in terms of PGI. So K into Fi PGI. So இதை நீங்க substitute பண்ணீங்கன்னா நமக்கு Fi PGI இப்போ தான் கண்டுபிடிச்சோம். I'm substituting here. So K times Ci dash, K times Bi dash PGI, K times Ei dash PGI square. So இதுவும் வந்து பார்த்தீங்கன்னா உங்களுக்கு in terms of rupees per hour கிடைக்கும். Fuel cost and energy rate. Next is incremental cost curve of received power factor. For thermal plants, the fuel cost is the main operating cost. It accounts for 60 to 70% of your total operating cost. So the following assumptions to be followed in incremental cost theory. The first assumption should be your input-output curves are continuous. So if you are keeping your input-output curves as discontinuous, it is not possible to calculate your input energy rate as well as cost rate. That is not possible in terms of your discontinuous curve. And the first derivative of input-output curves we are continuous. So it shows that we are taking first derivative only. And third one is incremental rate increases, increase in output. So I am going to utilize my cost equation. So Ca of PGI equal to Ai PGI square plus Bi PGI plus Ci PGI square rupees per hour. So the slope of the fuel curve cost is achieved by differentiating your Ca PGI one time. Just differentiating this corresponding equation one time. So if I am differentiating what I am get, the incremental cost I may achieve. Incremental cost is small change in input by small change in output. Tci PG of I by Tpgi. So the derivative should be 2ai times of Pgi plus Pi. If you are fixing your I equal to 1, 2 up to n. So the incremental cost usually denoted as lambda. So or otherwise IC. Some problems they are given as lambda, some problems they are given as IC. Both the notations are same only. It's nothing but 2 EI PGI plus BI rupees per megawatt hour. So this curve shows your linear relationship. So I'm approximated the incremental fuel cost versus output power curve as a straight line, as you've seen in your figure. It should be your straight line from your maximum power to minimum power. Should be a straight line only. Next, coordination equation without loss. Real-time example we are focusing. So now I am considering my two-bus system having two generation units. It shows that the two generators are connected in parallel, PG1, PG2. So the corresponding demand is PD1, PD2. The mathematical governing expression is I equal to 1 to 2 PGI. So only I am having two buses, PG1 plus PG2. Likewise, your demand I equal to 1 to 2 PDI. So summation, so PD1 plus PD2. So the optimization problem can be stated as C, that is minimization effect C equal to I equal to 1 to N Ci of PGI. C is nothing but your operating cost. I is nothing but number of generators on the bus. So subject to your H, PG1, PG2 up to PG1 is nothing but PD minus summation of I equal to 1 to N PGI. Next one, using the Lagrange multiplier lambda. The function of Ci conjugate is nothing but C plus lambda H. So L or C conjugate equal to I equal to 1 to N Ci PGI plus lambda times of PD minus lambda I equal to 1 to N PGI. So for minimum objective function, I have to differentiate the equation 12 with respect to PGI and equating to 0. So the cost function on the equation on the differentiate equating to 0. So dou C by dou PGI conjugate which is equal to 0. Right stands for 1, 2 up to n number of times. So Lagrangian multiplier introduced phenomena DC conjugate D dou PGI equal to dou L by dou PGI. So the cost, that is incremental cost, should be dou Ci by dou PGI plus 0 minus lambda equal to 0. So from this expression, we get lambda. So now lambda on the right hand side, you have only dou Ci by dou PGI only. So the lambda equation we are obtaining, that is incremental cost of the fuel. So if you are expanding up to n number of times, dou C1 by dou PG1 is equal to dou C2 by dou PG2 up to n number of times. Dou Cn to dou PGn, which is nothing but your lambda. For n units, we are calculating our cost of the fuel rate. Next one, the analytical solution of lambda. So here we are using Taylor series. So the cost function C equal to AI PGA square plus BA PGA plus CA. So I am using incremental cost to find the generations. So 2AI PGI plus BA equal to lambda. So PGI is nothing but I'm just bringing the PGI to the left hand side, rest of the terms should be the right hand side. So lambda minus BA by 2AI. So I stands for 1, 2 up to N. Now you substitute PGI in the power balance equation. So I equal to 1 to N, PGI minus PD equal to 4. So I am writing separately for your demand as well as generation. Lambda equal to 1 to N, 1 divided by 2 AI minus summation of I equal to 1 to N, BI by 2 AI equal to PD. So the overall lambda from this expression, the overall lambda should be PD plus summation of I equal to 1 to N, BI to AI divided by summation of I equal to 1 to N, 1 by 2 AI. So this is the final form of your lambda. Now you substitute your lambda in PGA in order to get your Taylor series expansion. That is f of lambda equal to PD. So while expanding your equation in terms of Taylor series, the final form should be del lambda of k equal to del pk divided by summation of I equal to 1 to n divided by 2ai. Yeah, the Taylor series expansion பண்ணிருக்காங்க. And when you have the incremental of lambda, you have the equation lambda k plus 1 equal to lambda nu, lambda k equal to lambda o. So this process is continued in order to achieve your specified accuracy. So only the continuity should be del pq is less than specified accuracy. Meaning I continue the next session. Solution by lambda iteration method without losses and with losses. It is a flowchart and algorithm perspective. Computer based one. உங்களுக்கு algorithm and flowchart pattern இருக்கு. சரியா? சொன்ன விஷயத்தையும் அப்படியே flowchart போட்டுருப்பான். Flowchart and algorithm. ஈஸியாக தான் இருக்கும். Next class பார்ப்போம். Once I completed the flowchart and algorithm, you have the economic dispatch control, your load frequency control, and integration. Single area, 2 area எல்லாம் பார்த்தோம் இல்லையா? யூனிட் 2ல. ஸோ அதை வந்து பார்த்தீங்கன்னா எக்கனாமிக் டிஸ்பேட்சில் கண்ட்ரோல் பண்ணுற மாதிரி கனெக்ட் பண்ண போகிறோம். சரிம்மா, ரிமைனிங் கண்டினியூ நெக்ஸ்ட் செஷன். தேங்க்யூ.